Chapter 10, Section 5, Problem number 19. All right, for the data in Exercise 19 of Section 2, test at the 0.1% level of significance whether, ignoring all other facts such as age, body mass, the amount of the medication consumed is a useful predictor of the blood concentration of the active ingredient. All right, several things here right off the bat. So we're going to be testing. So we're going to be doing hypothesis testing at this point. And it's the 0.1% level of significance. So here, our alpha is going to be 0.001. So this would have been 10%, 1%, there's 0.1%. Okay, so I'm at the alpha equals 0.001. Whether ignoring all other facts, okay, because in our process here, for this problem in 19, we were looking at the amount of medication consumed, and that's what we were going through, and that amount of medication gets us back to our beta 1, our predictor from our data, the beta 1 hat. So we're looking at hypothesis testing here. And for hypothesis testing means we're going to have to be looking at that 5-step process. So the first step in our hypothesis testing is determining our null and alternative hypotheses. And as noted here in this section, the null hypothesis is that we're at 0, and our alternative hypothesis here is that it's not 0. So that's where we're headed. Our second step then is identifying the relevant test statistic and its distribution. In this case, since we're in section 5, we can assume, which we shouldn't assume, but our best guess is the test statistic there is what we're looking after. So let's look here in the test statistic that is discussed here actually for hypothesis tests concerning the slope, beta 1, of the population regression line. And yeah, this we just mentioned. We're here looking at the slope of the population regression line. And that test statistic is t equaling the value of our slope of our regression line minus the value that we're looking at from the problem times what we have of our sample standard deviation of errors, epsilon, and that's divided by the square root of the sum of the squares of the x's. Okay, so here we're looking at if it's going to be significant at all. So our 0 is going to equal B1 versus beta 1 because we're looking at just anything being different. Not is it going to be more at a particular level or less from a particular level. All right, so then what we're going to need to do is actually calculate this t, actually calculate that. Now in calculating this, there's several things we're going to have to come up with. We're going to have to come up with our sigma epsilon, and that's a new piece from what we've been looking at so far. So what I did with that one, let's go back over to Excel here. Jump to Excel. And here we show, like I did if you had looked at problem number 11, I went ahead and calculated all the same pieces for a confidence interval for problem number 11 to have that data available. So the sample, or the sum of the squared errors, calculated that one, and that formula was the sum of the square of y's minus our beta 1 hat times the sum of the square of the xy's. And if you look closely here, you can see that the equation that we got set up here does have those elements provided there for that formula. So we have our sum of the square of the errors. We need that to be able to compute our sample standard deviation of errors, or S epsilon, and that's going to equal the square root of the sum of the square of the errors divided by our n minus 2, which is our degrees of freedom. So you can see here I've got the square root of sum of the square of the errors out of D34, which is the blue, divided by the n minus 2, which is our degrees of freedom, which I have in red over here as the G36. So that's 48. All right, doing that calculates the S epsilon for us that we'll need for our test statistic. Another thing we'll be needing is the because in step 4, we're going to be looking at this at our t at alpha over 2. And in this case, our alpha, let's go back over here like we did in problem 11. If you watch that, you'll see here we're going to put in our alpha, which we had noted was 0.001, dividing that by 2, which is going to give us 0.0005 for our alpha. So for t alpha over 2, we're going to need to find in our table t at 0.005 and go down to our degrees of freedom, 48, to come up with our t value. And in doing that, I got 3.505, and I have that in italics because that reminds me it's out of the table. I went ahead and, since I copied over from one sheet to the other, I've got the plus or minus term on confidence intervals, so I can look at the minus or plus side of a confidence interval if I wanted to do that. That's not necessary for the calculation. What is necessary for our calculations here was our step 3 in terms of calculating our t statistic. We had to come through and have some of the values that I already needed to calculate done, so that's why I went ahead and just copied that one over to do it. So here for our t statistic, what we had been looking at and written just a moment ago was we need our beta 1 hat. See, beta 1 hat, that's D26 there in the cell number, which is blue, so that's the blue, minus our B1, which in this case was 0, we noted, and that's divided by our sample standard deviation of errors, S epsilon. Let's see, S epsilon is in red showing here. That's in D35. Yep, there's S epsilon, what we calculated. And that's divided by the square root of the sum of squares of the x's. So the sum of the squares of the x's, this shows it's going to be in purple. Yep, up above there at D16, we've got purple, the sum of square of x's. So the square root of that gets me the equation to calculate that one. And I wind up with my test statistic being 25.52. Okay, we've got 25.52. We have the t alpha over 2 of 3.505. Let me jump back to where I'm drawing this. So all that, as I started noting here, is going to be calculated. And we did calculate t with all those other values. And that was 25. Let me jump back to Excel. 52. And then in step 4, what I need to be doing is compute the rejection region. And the rejection region, since we're looking at here around 0, I'm going to have 2 tails. Each of the tails is going to be that alpha over 2 on either side here. So at my alpha over 2, I may put a comma in there, alpha over 2, I had calculated that there in the, or looked that up. Let me pull that from the spreadsheet. That's this 3505. So coming back here, I'm at 3505, or minus 3505. So I'm at minus infinity up to minus 3.505, or 3.505 out to plus infinity. So there is my rejection region. And if we look at how we fit here, the t is definitely way out there in the rejection region. So we can reject the null hypothesis that the B1 does not have a prediction for our, so the B1 is not useful for predicting the value of the active ingredient. So X is not. And that gets me to the point then of saying, so yes. So we have a statistical significant at 1/10 of 1%, that the amount of the medication consumed does predict the blood concentration. Good. So as I'm looking back over the problem and jumping back to what I had noted up above here on the screen, once I had finished looking at the rejection hypothesis, I see that I wrote back up here that the amount of medication consumed is a useful predictor. Well, the amount of medication consumed is actually X, so that was our X. And then the blood concentration was Y, so Y was a function of X. And so in this case, we had our Y equals B1 hat of X plus B naught. That was our regression equation. So when I wrote B1 hat over here, that's the amount that our value X, the amount of medication consumed. So that X is that amount. So when I wrote B1 hat here, I probably should have read that one as X. And it's the B1 hat is the amount that the medication actually predicts the blood concentration. So that's slope of that line for our regression.